Microphones are dangerous with me because I'm already very loud, as some people in the audience know. So, hi. I did not make this talk fit the allotted time because I was aware that I was going first, and I'm also aware that one of the reasons why I'm here is because I'd like to learn more about the mathematical and computational advances happening. So I'm hoping that people will stop me when they don't understand something to sort of set the stage for how we go forward. I know I'll end up using jargon. It's almost impossible to recognize my own jargon at this point. So I'm more than happy to stop, pause, we can figure out where we're miscommunicating, and then continue on. And as Doug said, I was actually in that meeting 20 years ago. It was colder, right? I think it was colder. We were in... It was in the middle of summer. I still think it was cold because Minnesota. I don't know. 20 years is a long time. Who knows what was happening? But at the time, the field is 2002. We hadn't, France, who's actually here, hadn't yet done the first merger of two black holes. So numerical relativity was a bit stuck in desperate need of outside advice on how to move beyond our crashing codes, which were ubiquitous at the time. And that's where Doug came in because he was working with a lot of people to figure out how we can move forward. Gravitational waves hadn't been detected. And so since then, I realized looking back that my own work has completely kind of switched. And now I've always been motivated by gravitational waves as being a way of understanding gravitational physics happening in the universe and how we can learn about it. And numerical relativity for me was a tool to do that. So this talk hopefully just sets the stage, but I don't have any g mu nu equals 8 pi t mu nu in here. So we'll see how it goes. So in my opinion, right now we're living in very interesting times because we're here at that moment when we can actually probe gravitational physics, not as we think it should be in theory or in Einstein's theory, but rather how it really plays out in the universe. So for buzzwords, gravitational wave astronomy and multi-messenger astronomy has arrived. So multi-messenger astronomy means that we can probe astrophysical phenomena in the universe via gravitational waves, electromagnetic waves, and particles like neutrinos. So that's that buzzword for the combining of all of those things. That said, I'm not going to talk about that because I like my simulations to be very clean, so I'm going to stick with vacuum binary black holes, so there won't be any matter in the solutions I study. It's a simpler world, and also it is the world of black hole binaries, black holes that are in a bound gravitational pair that are spiraling and merging around each other. So now we have a situation where we're seeing these, literally observing black holes that are merging routinely in gravitational waves. So the LIGO observatory is actually detecting binary black holes more than once a month almost, right? It's an incredible time where we can't even keep track of all the binaries that are out there. And so we're also, as I think as a numerical relativist and plan over the next 20 years, the thing to think about is where we're going in future gravitational wave detectors. So we have one, two in the United States, one in Europe, and one coming online in Japan pretty soon. But we're also going to have future ground-based that are better, and we're going to have space-based gravitational wave detectors. So all of these things put requirements on how good we are at solving our equations that govern these binaries and the emission of gravitational waves. And so that's what I'm looking at when I see what's motivating the work. So numerical relativity itself, which is the study of Einstein's equations, solving the Einstein's equations in their full generality, we're not making any linear approximations to solve the solution, and I'll talk about what that means in a second. So that's what the field of numerical relativity is, and it's how we predict what the gravitational waves from these systems look like and what we use to interpret the gravitational waves. So they're vital to the success and strength of gravitational wave astronomy today. I'm not going to talk enough about this. I'll mention what it means for me, like what I would like people to solve and when they do computational methods of numerical relativity. I usually am looking for others to solve this. It's not my primary work, but I'll mention a couple challenges. I think we'll get to that as the workshop moves on. So I'll start with a cartoon to kind of keep it, we're supposed to be awake. It's early and it's really nice out, so it's hard to be inside right now. So this is from a comic strip called PhD Comics, and this is how they describe two bodies in gravitational waves. So when we're doing a linear theory like Newtonian physics, like this institute, we can use superposition of solutions, so the two-body problem isn't much of a challenge. But when you do general relativity, which is a nonlinear theory, the two-body problem is a huge challenge. And it was such a big challenge that it took many, many years to actually be able to solve it routinely. So this is why two bodies are so interesting for gravitational waves. So here are two bodies. One's a black hole. One looks like maybe it's supposed to be a neutron star or something. And the gravitational waves are produced when masses accelerate. So that's what a gravitational wave is. A non-uniform acceleration of mass causes an oscillation in space-time. Everything with mass and or energy can make gravitational waves, so we can do it by moving our arms, but we're not going to do it very successfully. That will be too weak to ever detect. So the best thing is to have two bodies, large, and the two bodies being more compact, the better, which is what makes black holes the ideal source of gravitational waves. So if these two are dancing around each other, they're causing ripples in the fabric of space-time, but they'd be so small. So what we're going to look at is the more massive, the more energy generated. So black holes in a binary system are a nice source of gravitational waves, as we've historically seen now over the last few years. No jargon yet? You can flash a jargon card. So this was the very first detection of gravitational waves back in 2000, and well, the event happened in 2014. It was announced in 2015. I had happened to be in the LIGO collaboration nicely enough for 1 year, and you have to be in the collaboration for 1 year before you're on paper, so my timing is excellent, I have to say. So this is the Hanford, Washington State Observatory, and this looks ridiculous, right? All that time and money for a really ugly sine wave, but nonetheless, this is exactly what a messy merger of two black holes looks like. So a couple of things that are going to be fun to look at here is how messy this amplitude is. This is something called strain. This is how much length along the arm of a detector is changing over its total length. So it's unitless. And this is time. So this is happening really quickly. So that gives you a sense for what these ground-based detectors are like. They catch the very end of what had been a long, long history of two black holes orbiting around each other. And then you get this last 0.2 seconds where they merge and the detector catches it. So that's my motivation. I wanted to see this happen. I was fortunate enough to see it happen for the first time. And now it's about getting better and better at this, and what does that mean for the implications of the field. So this is what they look like to give us now a bit more fill-in of all these words I'm going to use. We'll tend to use the word inspiral, merger, and ring down. This is a description of what dynamics are happening as the two black holes are orbiting each other. So they've been orbiting for a very long time. At some point, it didn't matter if it was GR or not, general relativity, because they were too far apart. So we call this part the inspiral, where the two black holes are in orbit and separated. We call it merger when the two black holes are just about now forming a single body, which is another black hole. And we call it ring down when we're going down, we're getting rid of all the interesting radiation, because we're now becoming a single curved black hole, which is a single spinning black hole which doesn't give off any more gravitational radiation in isolation. So that's what's called ring down. And the reason it's called ring down is it acts like a bell. If you hit a bell, the frequency, the tones of that bell is related to the bell itself. And the same thing is here. If I smash a curved black hole, then the way it rings, the gravitational radiation is indicative of that, the mass and spin of that black hole. And then this is what all the fuss is about, is this gravitational radiation. So the inspiral phase is described by what's called a chirp. It's an increasing frequency. The merger phase is this transition, basically, from the chirp to something that will exponentially decay. And the word template means it's what was used to actually make the detection. So they had to have a library of waveforms, that each waveform is somehow subtly different depending on what the initial parameters were of the black hole binary. And that was used to detect the first gravitational wave. I put this in because I want to use it to explain the difference between these regimes and how we solve them in general relativity. So this is the velocity of the two black holes. It looks like, you see here, they're separated at this point, and this is where they merge into a single black hole. And it looks like they keep going, but that's just because we're tracking something that doesn't make sense once they merge. So you can ignore that part. But what you can notice is that they're really moving quite quickly. So these black holes, right before they collide, are moving at a significant fraction of the speed of light. And that's important when we talk about how we actually solve Einstein's equations to understand these sources. So here's my cheat sheet of the two-body problem in general relativity. I'm only going to worry about this one at the end, but here's the other two paths. So we can break it into three regimes. That in-spiral regime, when the black holes are far apart. As long as the black holes are moving at a fraction of the speed of light, and as long as they're pretty much able to be described by a point mass, you can use post-Newtonian theory. And then you can use it beyond there. So at some point, post-Newtonian theory starts to break down, and you would need full numerical relativity. But that's a mushy boundary. So there's a very good handle on how to understand the gravitational waves from post-Newtonian theory for the two-body problem. The other regime would be the perturbation regime, which would be that you can describe this space-time as a single black hole, like a Kerr black hole or a Schwarzschild, that has a perturbation, that second black hole is a perturbation on that space-time. So that means that the second black hole has to be significantly smaller than this one. So it has to be what we'd call an extreme mass ratio. And then you use the self-force. So this guy is negligible. And this is also very well understood. This would be the regime of early in-spiral, and this would be the regime of ring down, once you've got that perturbed single black hole that's settling down to its final state. And then this is the world of a lot of us in the audience, numerical relativity. This is where neither of those things are true. So you don't have such a the separate mass ratio to do perturbation theory. They're too close in mass, bless you, and they're too close together. So you can't use the post-Newtonian approximation. So that's what we'll call numerical relativity. I tend to call it strong field, and what that means is that the curvature, what's happening, is large, so you need to account for the full general relativistic effects. So I might also use the word full GR. Nothing? Tough crowd. OK, so hopefully you're still with me and awake. So to put it in context of this, and this is terrible because it's hard to even explain what all that stuff is, but you put it in context of the gravitational wave detection again. If I took a Fourier transform of a waveform that I just was showing a couple slides ago, and I pick a total mass of the binary, so now I have to give these black holes units. They could be two black holes that are 10 times the mass of the sun, or they could be hundreds to millions, depending on what frequency range we're looking at. So if you look at how these waveforms would behave in the band of the detector, so that's what this is, this black line here with these little modes sticking up. And this dotted line are the early LIGO wave, expected noise boundary, and then the one that we're working towards right now that hasn't been quite achieved yet, but should be soon. So what that tells you is that's where the gravitational wave observatory is sensitive to some signal coming through. And then these are the predicted signals from numerical relativity. This was two black holes in-spiraling, merging, and ringing down at 242 solar masses. This is what it looks like if you do a lower mass, 61. That means 230.5 solar masses combined, and then it merges and ring down. And this one's if it's 24, a much slower mass system. The reason why I show this is to help people understand that in general relativity, when we do that, because it's a vacuum simulation of two black holes, so there's no neutron star or matter, there's nothing else there but just curvature, we can completely scale our solutions to any mass. However, when you have a detector in the room with you, then that detector is only sensitive to certain frequency bands, which means that as I make the total mass higher, the merger of the signal, that peak is moving. It moves to the left in frequency to lower frequency. How big this number is, this is signal to noise ratio, so how strong the signal is. The further away the binary is, it will drop in amplitude on this plot. So all those things matter about what we can see in the universe and what we can't see. So we found, surprisingly enough, in these early days of gravitational wave astronomy that there were a lot of bigger than expected black holes in this mass range. So you see 30 solar masses to 80 solar mass black holes colliding, which has been fun as an astrophysics question. And another thing to keep in mind is that these black hole collisions emit a lot of energy. It's just energy in gravitational waves which we can't see or feel. So these black hole collisions can emit as much gravitational radiation energy as a star does in light during its entire lifetime. But we're completely blind to it until just a few years ago. Yep? This dotted would be the observable signal. So the frequency, yeah. Right, so since this is at 100 to 1,000 hertz, that means that it's sensitive to signals that are about 100 solar masses down to a few solar masses. So I could do a binary neutron star. 2 neutron stars would be right here. So if I do if I went to a space-based gravitational wave observatory, that would be super low frequency. These things wouldn't be seen on it, and you'd get 10 to the 1,000,000 times the mass of the sun binaries, because that would make it a really low frequency. Is that better? Yeah, because I don't know what could be confusing, so please feel free to interrupt more so we can get our language down a little bit. I will show this slide. This is to take that picture of the two-body problem and saying that we know we want to solve Einstein's equations because we want to be able to predict and interpret these binary black hole events or neutron stars. We have to know what the landscape is, the theoretical landscape of solutions, to know where to spend our time. So if I plot something where this is the separation of the two bodies, we'll call them black holes, from, they can be pretty widely separated to on top of each other, and then this is the mass ratio. So in that one slide of the two-body problem, I said you could have two black holes that are very, very different in mass ratios. That'd be down to here, and that's that perturbation theory, gravitational self-force regime. When they're widely separated and not moving too quickly, that was that post-Newtonian regime. And here is the regime of numerical relativity. These boundaries are what's interesting in the future for computational advances in numerical relativity, because it's where we don't have solutions. So a big, big problem, probably the biggest, if I were going to put one stake in the ground and say if I want something for Christmas, well, actually, it could be my next 10 years of Christmas presents, honestly. It would be a code that could solve this regime. So we have a problem in that there's some expectation that the universe will have black hole binaries where one black hole is a few hundred to a few thousand times the other. And there's a gap between what we can do realistically in numerical relativity and what perturbation theory can do. So this is a huge regime of interest for people who can write clever algorithms to capture that. So it's not something I think personally that you could just throw more of what we do today on top of this. We won't get there without clever advances. So that might be one of the topics we discuss throughout this week. Another one is this is a hard boundary to define, the one between post-Newtonian and numerical relativity, because it depends on what the parameters of the black holes are. So if they're non-spinning and they're equal mass, they overlap. But if they are eccentric, which means the binary is not circular, the orbit, if they have high spins, then this widens. So this is a moving target depending on the parameters. Yeah, Warner?
Just clarification.
Please.
So you're saying it's difficult in that green area between numerical relativity and perturbation. Is that because you have to integrate for a long period of time?
Yeah.
Your codes? That's the point. Right?
Yeah, right. So here, actually in both of these green regions, and anyway, so here you can imagine that the black holes are moving slower. So that means each orbit is taking longer. We're adding up truncation errors. We're getting very inaccurate in this regime. Here, the problem is that I have to resolve the little black hole. And that's becoming prohibitively expensive. And we're also doing many orbits. So this region is almost more adding up just orbits is challenging. And this region, resolving that little black hole and still resolving the gravitational radiation. So our problem is that we have to do the black holes themselves because there's a singularity in the middle of this. I'll talk about that in a second. So they're really hard to resolve. And then you have to get the gravitational radiation at the end of the day. So you don't get away with murder because you still have to be able to resolve the gravitational radiation as it moves towards spatial and temporal infinity. So that makes it challenging to get that right. And if we don't get that, there was no point in solving the problem. So thank you, Warner. Yeah. I like team. Okay. I do this because we need to wake back up again. I love this thing for 2 reasons. Well, one, I did steal it from Pablo a long time ago. But anyway, I like this because back in the 1950s, apparently people actually wrote down everything that was said in a conference. We don't do that anymore, maybe for the best. I don't know. But I'm intrigued by this. So in 1957, they were in the first GR meeting in North Carolina, Chapel Hill, in the United States. And Charlie Misner was talking, and Bryce DeWitt's often credited, I think, with sort of inventing numerical relativity, or the concept that we were going to use a computational solution to this problem of the two-body problem in general relativity. And I like this quote for a lot of reasons, because he's talking about how we're going to solve the two-body problem, and he's going to assume we have a computing machine, which is cute, better than anything they have now, and many programmers and a lot of money, which is still true. We still need a lot of money and programmers. They're going to solve an initial data problem. So this is the metric. That's the space-time metric describing basically distances between points in a curved space-time. This is its time derivative. And so this is an initial value problem. You're going to solve it at t equals 0, for instance, and then there's evolution equations that will take you forward in time. And either the programmer will shoot himself or herself, or the machine will blow up. And no one died in numerical relativity. And so we're past this hump. So I'm very happy that after, I don't know, it's a long time, 2005 from 1957, it's finally been solved. So the two-body problem of black holes took decades and supercomputers. So this quote wasn't ridiculous back in Charlie Misner's quote in 1957, but maybe underestimated the challenges we were going to face in the field. I usually blame Stu Shapiro and Saltykowski because in 1985 they said that this was the holy grail of numerical relativity, which I think is a mistake in any field to call yourself a holy grail. A code that simultaneously avoids singularities, handles black holes, maintains high accuracy, and runs forever. In some sense, this has been achieved. The singularity part is what makes these black holes unique computationally, because a black hole is something where, yes, not even light can escape. But when you're thinking of a computer, it's a place where there is a region of infinite curvature sitting there, and computers hate that. So that's what makes black holes in particular challenging to solve. But we know how to do it mostly. This is a little cartoon because despite all of this complication, black holes are the simplest things in the universe, really. That's why I like them. Neutron stars are hard. They take all of Landau and Lifshitz to solve. But black holes are described by 3 things as long as they're isolated. How much angular momentum, how much they're spinning about their axis, how much mass they have, and maybe charge. And I cut that hair off because we usually assume black holes are neutral when they're in the universe. So that was just to contrast how complicated this two-body problem is with how simple the one-body problem is for black holes. So the problem got solved relatively famously in 2005 by our own Franz, who's in the back of the audience. So I'm going to let him talk about all the hard stuff, right? Yeah, okay. He can tell you about his code. So this is what the problem famously was drawn by Kip Thorne for a long time, that we knew how to do this inspiral part because it was the regime of post-Newtonian, which I already told you about. And we knew how to do this part, which was the regime of perturbation theory. And I don't know why Kip thought this was going to be so interesting. But we did not have the regime of supercomputer simulations of numerical relativity. And then Franz came up with the first solution of 2 black holes, making it through merger and ring down. And this is a slice of what the gravitational radiation would look like as a slice in space at an instant of time. It looks like an inspiral pattern. You'll see this again. This was the second approach. I think psychologically speaking, once one person proves it's possible, it really becomes much easier for the rest of the field to do it. And in a completely different manner, 2 groups at the same time. In fact, they gave back-to-back talks at a conference, which was awkward when you realized what was happening, that they both had another solution. RIT and NASA did the moving punctures approach. They have a very different way of handling both the black holes and the equations. And after this, it took about a month for the rest of us to solve the problem. So it was completely a revolution in the field. Why did it take so long? Well, you can ask Doug. We really didn't know what we were doing now. It took a long time because Einstein's equations have a lot of flexibility in how you describe them. So you needed to have this well-posed set of hyperbolic equations for these nonlinear set of partial differential equations. So there was so much freedom that a bad choice would lead to runaway solutions that then cause the computer codes to blow up, basically. And there's also something called gauge conditions. So there was just how you chose your coordinates, how you formulated it, was just almost a sheer amount of freedom was too much. And the simplest way to do it was not a good way. And so it needed some more advanced technology, mathematically speaking. And also, it needed computational infrastructure. So you couldn't just use a normal uniform grid where you just slice up your space and run. It had to have enough mesh refinement. So it had to have a way of resolving down where these singularities are in order to solve the problem. So there were kind of two competing things that had to be solved at the same time in order to be successful. But finally it was. So this is just the recipe. I mean, I'm not going to go into all of this. I think we could. This might be a point for people to say that they're interested in a certain aspect of the problem, and we could dive into it more. But this is sort of a recipe list of what's important. You had to figure out that mathematical formulation of how you're going to write the equations down, how to specify initial data. That's still a big problem. So we're always at the mercy of what we set up, that t equals 0 solution before we evolve forward in time. The evolution equations themselves, so this is our basically the equivalent of our vector potential and electromagnetism and an evolution equation for that. Then we have to choose our coordinates, which are changing with time. This is the one I mentioned before that's unique with black holes because they have infinite everything in their center when you approach that singularity. There is an event horizon which famously shields the singularity from the outside universe, but to solve the equations we have to do the inside as well. So we don't, it's not, you can take advantage of the fact that there's a horizon separating physically, but it's not quite so simple. Then we have to extract the gravitational waves, which this is an example, and do all these other things like parallelization. So this is a snapshot of mesh refinement in case that word is unknown to the audience. It means that I have many grids, and as you approach the little black hole, so this is one black hole, this is a bigger black hole, you can see that you have more and more refinements there than you do out here. So this would be where I'd be extracting this gravitational radiation. This is along one line of sight. So the gravitational radiation is really a three-dimensional tensor. And then very far away from where the two black holes are merging, you would actually do a line of sight, and you would see this gravitational waveform that's typically shown. So that's what we're trying to do. Of course, it's always more complicated than that, but what basically the point is that you have a lot of parameters when you start this game, when you're at the initial data point. You've got the two black hole masses. They each have their own spin vectors, which could point in any direction. They could not be circular, so they could have eccentricity, etc. And then at the end of the day, they're going to have some mass and spin. So they get very simple. And maybe gravitational recoil, which we'll talk about in a second. And all that information is encoded on these gravitational waves, which I said is this 3D plus time object that we translate into a single waveform depending on the line of sight of our detector. And we always show you this quadrupolar mode called L equals m, m equals 2, because we use something called spherical harmonics, which is the same thing you'd use in quantum mechanics, to specify an angular, it's basically just a basis function in angles. And we do it because it's easy. And then the 2, 2, L equals 2, m equals 2 is the dominant one because we're quadrupolar radiation and general relativity. And so we're plotting these coefficients when we show you gravitational waves. But of course, there's more than that because we excite all these other modes too when we study gravitational radiation. So there's some complication there. And then we tend to solve this beautiful mathematical creature called psi4. But what the detector likes is strain, so you have to take a couple integrations to get there. But that's basically what we do. Set up initial data, solve it, and then produce gravitational radiation that's a function of the initial parameters. So the state of the art as a production of waveforms for the consumption of both gravitational wave community and astrophysics community comes down to basically 3 public catalogs. So those are the catalogs that different teams have released to the public for anybody, not just LIGO. Basically what they are is the Georgia Tech group, the SXS, which is the Cornell, Caltech, et cetera team, and RIT. And And we release these waveforms to the public so anybody can go do science if they need these solutions of Einstein's equations. And we specify the two masses of the black hole and their vectors, produce the gravitational wave, and add the waveform to the catalog. So they're not, this is like a picture of what it looks like. Each dot here would be a different numerical relativity simulation. And I put this in, even though this is very old now, because you can see that it's not continuous. So we haven't covered the full space. Not only that, it's very, very hard to make the second black hole much smaller than the first. So Q equals 20 is about the limit of what you can find out in the public arena for gravitational waveforms. Also, it's hard, these spin vectors. So as you change the spin orientation with respect to angular momentum vector here, the plane, the orbital plane will precess, and also the spins can precess. So things get much more complicated as these vectors go away from being parallel to or anti-parallel to the orbital angular momentum. So all those things are just complications. End of the day, it just means we don't have a complete description of the whole parameter space of these binaries. So that's still a work in progress. We're still all putting out waveforms and trying to improve things. And that's separate from the fact that at this point, we still can't go beyond a certain mass ratio and a separation. So the SXX group has some of the longest waveforms, and by long I mean if the black holes are farther apart on that axis, they take longer to merge. It has more gravitational wave cycles. It's harder. So that also is a struggle for the codes, for the same reason Warner was asking about earlier. How is it used? I said I would do the impact because that's what I've spent my time thinking about. Probably the number one use of these gravitational waveforms is templates. So here's another PhD comic cartoon. Now you know how I think. I wish I could draw and do this myself. So the idea of this is that each one of these people are talking in a room, and you're trying to hear a specific signal. Then what you could do here in match filtering would be you would have a whole library of different binary black hole waveforms, and you'd match them all to the signal to figure out what the signal is and what parameters it has. So that is the go-to. It's not the only way to check gravitational waves and interpret them, but it is it's the strongest way to do it. So that's the most used way of numerical relativity on gravitational wave astronomy. There's a lot of other things, only one of which I'm going to tease out and talk about because we could be here for a long time. But things like testing general relativity to see if it's the correct theory of gravity for the universe. Numerical relativity provides very nice ways to connect the initial data, how those black holes in their binary before they merge, what do they look like, to how they look like at the end when there's just a single black hole. Those ring down modes I mentioned, as you settle down, give you nice tests of general relativity because they predict an Einstein black hole should behave. So you can test whether that's the real one. This stuff is all in its infancy. So there's no smoking gun yet. Everything's consistent with Einstein's equations. But it's certainly one of the places to pay attention to because very exciting work's happening. And I'm completely ignoring all the fun with neutron stars because there you do equations of state and all sorts of things that you can't uncover in a terrestrial lab because neutron stars are so compact. They reveal whole states of matter that are unattainable on Earth. So I'm going to pick a topic and play with it. Maybe this gets too technical, we'll see. But one of the first fun predictions that happened in numerical relativity. So we spent all these years trying to solve these equations. And it turns out that the gravitational waves look pretty smooth, unlike Kip Thorne's original cartoon. But there was one thing that was way more interesting than people anticipated, and that's called gravitational recoil. And that's what happens is that if you have an asymmetric system, so say unequal black holes, unequal masses is an obvious example of that. When they're orbiting each other, the asymmetry will average out. But when black holes merge, they do it very quickly. And so at some point, when you have like an unequal mass system, when they merge, you're left with a net linear momentum in a particular direction. And the consequence of that is the black hole that happens, the final merged black hole, goes off in the opposite direction to conserve momentum. And that's called gravitational recoil or kick. So what happens is, as you inspiral, the center of mass stays pretty constant in velocity. But when you merge, if you had some asymmetry, you're left with a large amount, well, relatively large amount of net velocity. So net linear momentum in one direction. And what happened here is that because this effect is most important right in the last orbit, right when you merge. It was something that post-Newtonian could see but couldn't predict the full magnitude of. So this was an early, exciting result from numerical relativity. So the remnant black hole, the thing that's left after this merger, not only has mass and spin, but it can have a velocity associated with it as it wanders outside of whatever bound system it was in. This has not been measured, neither electromagnetically. So people look for, believe it or not, people look for traces of a black hole moving through gas that could exist in the universe, nor has it been measured in gravitational waves. So these kicks are revealed to us, potentially, by interactions of these modes I mentioned earlier. So we have to pay attention to coordinates, which I hate, if I'm honest. So here are two black holes, and we've been talking about the way they might spin and their masses and their angular momentum, but the detector is going to be looking here, where the detector is. So we have a line of sight, in reality, to the binary itself from the gravitational wave detector, and that black hole could be moving off in any direction, depending on what the initial parameters, way the asymmetry was in the initial parameters. And the way we can study this is by understanding the different radiation modes. So this is one polarization of gravitational waves, and this is looking at the gravitational radiation along the line of sight, depending on if the binary was, the orbital plane was, if this is LIGO here on the floor, like its big L-shaped arms, if the binary orbit was face on or tilted to the observer. And then what happens is that causes there to be different modes that get excited, and it changes the amplitude. So if you include a bunch of higher modes, so all the different fun things we could have from the theory, you get very interesting effects here, which is basically giving us a way of making a measurement of gravitational recoil at the end of the day. So in this work recently, we found that if the first gravitational wave detection was really boring, I mean, it was really exciting because it was the first detection, but it had equal mass non-spinning black holes. So it's the very simplest system. And so if I had a very simple system, if I studied this inclination angle I just mentioned versus an orientation to the detector, I can't tell anything. It all looks the same. Okay? In fact, an overlap 1 means that I could not have a template, one of these waveforms, at different inclination angles. They would all look exactly the same as the detection. So we're completely degenerate. We can't tell the difference. But if you have an asymmetry in the source, like a q = 3, that means one black hole is 3 times the mass of the other. Suddenly, I can tell the difference between orientations of the binary. And so now I actually can say here is where the signal must exist. It can't have any of these other inclinations. And that allows us, for the first time, to say I can tell the difference. I can read off the gravitational recoil along the line of sight of these binary black holes to some error. So what this tells you is if you know what the answer is, it's called an injected signal. If I say it's 114.5 kilometers per second, then the detection algorithm would give you error bars. And you would know it's about 100 kilometers per second plus or minus 15 kilometers per second. So we can actually measure gravitational recoil potentially with LIGO. This has not been done. This is us saying it's possible, but the detector isn't quite good enough yet to do this. Or we haven't seen that kind of source. You still can ask questions. The other fun thing you can do along the same thing, looking at asymmetries and figuring out how it can inform you about what's actually happening in the universe by only using gravitational waves, is called a double chirp. So I remember I had this picture from France earlier, which was that gravitational radiation at an instant of time if I took a slice of it in space. So here is an in-spiral. That's that in-spiral pattern. That's what that gravitational radiation looks like because it's quadrupolar. And then you have the black hole is going to get kicked, as I said. So it could either, the observer is in this direction. If the black hole is being kicked in this direction, it's coming at the observer. And if the observer is off direction, then the black hole will be moving away from the observer. And because there's asymmetry in this signal, you actually will see different signals from the gravitational wave. This is called a time frequency plot. Basically, it's a Fourier transform, but in bins. So you're seeing how much time the signal spends at each frequency bin. And this is what it looks like if I'm in this direction. If my observer's here, but my black hole was kicked this way, my observer's over here. The black hole's always being kicked this way. So if my observer's sitting here, it only sees this strong signal as it sweeps by. So imagine this in spiral moving in time. Then this is corresponding to this bright spot here. But if my observer is in the same direction as the gravitational wave kick, I see two bright spots, here and here. And this is what we call double chirp. So this is our prediction of the fact that you'd see these asymmetries actually in the signal itself as they inspiral. And that if you can see two bright spots, that would be indicative of the fact that the binary black hole must have been very unequal in mass in order to produce such a strong double chirp signal. And it's called chirp, if you're wondering about that, because this increase in frequency with time is indicative of a inspiraling compact object. So that's called the chirp signal. If I could whistle, I would whistle you a chirp. I can't, so it's just an increase in frequency like a bird chirping. And this means you get a double peak because you had, because of the asymmetry of your orientation, you would see potentially two chirp signals in a row.
Can you just explain that a little bit?
Because it's only you, Warner. Everyone else understands it completely. I don't understand what happened. I'm just kidding. You know it's not true. Just like teaching. You know the entire class is lost.
I asked this because everyone got it.
No, they didn't.
But it's just the mechanism for getting a double chirp. So
Yeah. Oh, what's the mechanism? Sorry. Sure. So let's use the little cartoon on the top. Actually, I have to admit, it took me forever to understand what the postdoc was talking about when he did this. Han. I was like, what are you talking about, Han? So here's the black holes. This one's the small one. And they're orbiting around each other. And what's happening is, at the end, they'll merge, and the final black hole is going to move off in one direction. And we're going to call that kick on. It just means that the observer is sitting in the same direction as the kick. So there's two things that impact this. One is you have to have an asymmetry in the gravitational radiation. And two is it depends on where the observer is sitting. So the observer will not be able to tell there was a kick if he's sitting off, right? He's not going to know the difference, or she. So, well, LIGO's actually an it, isn't it? So then that's causing this. So what's happening is if you're lucky, you have to be lucky, if you happen to be sitting, the detector is looking in the line of sight where the black hole is coming towards you, then that particular configuration allows you to see this second signal because you have time to see two kind of bright spots in amplitude rather than just one if you're opposite direction of the kick. But it is tricky. I struggle with this thing.
Why is it that you have
Two?
Yeah, I need the figure in the middle.
The sky is eclipsing.
The horizon is
Highly distorted.
The final black hole is highly distorted, just like that. So
Peanut.
that is the one that produces this asymmetry in the imaging.
So what we're talking about is that at some point, the two black holes are just merging into one. Eventually, they're going to form this sort of almost spherical horizon late in the day. But in that, for just a short period of time, you have this highly distorted horizon. And there is signs, and this is not theoretically completely done, but there are signs that if you have this highly distorted horizon that mimics in the gravitational radiation, you'll see it. So you actually have this opportunity to have different spiral pattern because of this bulge that's happening here in the horizon. And as that bulge, it beams towards you. So there's a distortion in the horizon, and as it rotates, you get a beaming effect from it. Please, sir.
Well, in space, of course, in three-dimensional space, what's the observer in any other direction than exactly the direction
Yeah.
that always looks in that direction?
So if you're in the opposite direction, you'll see nothing. If you're literally in the opposite direction, as you go off here, it gets weaker. So there'll be a peak. The best scenario will be if you're directly on. And then as the observer goes away from being in the direct path of the kicked black hole, that signal will weaken. Absolutely. Until it's nothing as you go completely opposite of the kick. Also, the way this signal will change is it will be stronger for a more highly distorted horizon. So as the mass ratio difference increases, one black hole is much bigger than the other, you'll peak that way. And at some point, it will disappear again. So you have these two effects. So it won't be easy to see it won't be ubiquitous. Every signal is not going to have this because there is that also that luck of where you are observing. But it is fun to think that you actually have a distinct signal that you could look for that would indicate this. Yeah, that's another complication. So the other complications Paul was mentioning is this. So if you have, again, if my LIGO detector is in the floor, if my orbital binary is oriented such that my binary is like this, you won't see anything. As the orbital binary tilts, you can see more gravitational modes in the signal, and then you can detect this better. So there's a lot of things happening to see this. So why bother talking about it? I think we've been such in the beginning of gravitational radiation that there's almost this naive picture being painted of this, of what, we always talk about the binary as if it's always going to be parallel to our detector. And that's not true. And as we get better at gravitational wave detection, we're going to learn more and more about the actual binary that's excited these gravitational waves by being a bit more sensitive to all these nuances in our orbital plane and directions of line of sight, et cetera.
So I have a much more elemental question. What the color is plotting what quantity?
Oh, here or here? Both. This is, if you can see these axes, they're very helpful. One says X code length and one says Y code length. So you know but this is literally just an XY slice of the gravitational wave, and the colors is the strength of the gravitational wave strain, basically. So it's stronger when it's a darker blue color. But it's in a unitless thing, so it's just a magnitude.
How does the strain a function of position?
This is the in spiral, so this is the actual gravitational wave amplitude along a slice.
At a certain moment?
Yes, at a
Point of space?
well, this is a slice of space. So yeah, this would be at that point of space. That's the psi 4 at that moment in time. So we took a slice. It's a 3D psi 4. That's a movie if you did the whole thing. And then at that instant of time, this is a two-dimensional slice of that gravitational wave. Psi 4. That's right. And this is just an XY slice of that at an instant of time. So to understand it in this plot, which has time in these units, then you have to allow this to move, because this is only one instant of time. So this is like a slice here. And then you'd have to wait till this thing spun around again, and then you'd get this second slice, because this has units of time in it. So here, the color map here is, again, plotting strength of the signal, but now in terms of how much frequency is spent at each little time bin. So this is what it looks like if you were doing gravitational wave detection. They like to look at how you can sit there and see how much frequency, how long you spent each band. More?
And unfortunately, the time step, the time over there, that it says what, 170 something?
Oh, you can read that, 129.70 M.
29 doesn't match the time here in this plot. The poster put the 129 is from the beginning of the simulation, and here the time 0 is when the black hole starts.
Yeah, that's true. If no one, well, we do have a blackboard. So if I were here, just to give you a sense of time, if I were doing my gravitational wave like this, what this 0 says, this is time, this is t equals 0. So you force the merger, the peak of the signal, to happen at t equals 0. So that's just a shift in coordinates. Yeah?
This slice is what the face-on observer would see.
Yes. Right, so exactly. So if I were sitting like this is the plane, and we're in our position, that's what we would see. And then the question is, if you can tilt that orbital plane, and instead I started looking in this direction, I would see different modes get excited. I could reveal these patterns. But if you're face on, you won't see it. That's right. So the two effects are, where are you oriented compared to the binary when you take the measurement? If you're face on, you won't see anything. If you're in the opposite direction of the kick, you won't see anything. But if you're moving towards the kick, then you'll see something. It's complicated. Oh, yeah, I'm switching scenarios out, so let's stop there for a split second. Does anyone else want to talk about this? It's going to get easier now, again, for me. Maybe not you. because I want to know when all this is going to happen. So this is a slide on when to expect things to improve from the gravitational wave point of view now. So right now, we are in LIGO's and Virgo's third observing run. So the O means observing. The 3 means the detector has been shut down twice to improve. Okay. So the first detection happened here. The neutron star happened here, and now we're in the third observing run. This is 120 to 170 megaparsecs. So that's how far away you could see 2 neutron stars colliding. So that's well outside our galaxy. That's in our local group. You can see binary black holes further away. But so the Virgo is also in its third observing run. This is the European detector. Kagra is a Japanese one, and it's expected to join with the other 2 late 2020. Why this matters, if there'll be a third detector, is that you can start to point on the sky better. So right now, when LIGO and Virgo make a detection, like, oh, there's a binary black hole over there. It's a very large swath of the sky they see. And astronomers see tons of galaxies there, so that's not very helpful. Every time you put another detector on the list, you make that pointing better. And so you should expect to reach that design sensitivity we're talking about in just a few years by all 3. So that will be an exciting time for these detectors. But I care about what I have to do to get the science out of those. So first, let's picture a broader set of gravitational wave detectors, and then we can ask ourselves, how hard do we have to work to be able to see all these? So here is the pulsar timing array. This is something that uses actual neutron stars that are in the universe spinning and looks at how gravitational waves interact with those things to measure gravitational waves. This has not happened yet. This thing is running, but we don't have any gravitational waves detected yet. This is the regime of LIGO that we've been talking about, where we've seen all the detections. This is frequency again. Again, this is how much the detector changes based on the gravitational wave impact. This is LISA. This will be a space-based mission led by the European Space Agency, junior partnered with NASA, the American Space Agency. And so this one is going to have a different frequency band. That means it's sensitive to different black hole binaries. So that's something we're very interested in happening. This time scale is now, 2030s. So I'm going to skip that. Can I skip this too? No, I won't skip this. So what this is tells you, why would you care? Well, you guys might not if you're not interested in astrophysics. But what this LISA mission will do, or a future ground-based detector called Einstein Telescope, is that we've been talking about solar masses that are here, like 10 times the mass of the sun, 60 times the mass of the sun. This goes all the way up to 1 billion times the mass of the sun. And it can see really, really far away to basically the beginning of when we believe there could be black hole binaries out there. So these space-based and future ground-based detectors see all the binary black holes merging, basically, in the universe. So that's why we're excited. And we're excited because that's possible. And so what you would look at if you plotted these same gravitational waveforms we've been looking at, and this is a very complicated plot, I understand. But what you would see is if I took one, let's just grab one of these. Let's just grab this light blue one. This is LISA. That's 2034 future space-based gravitational wave detector. Here's LIGO right now, this light gray one. And then I would be able to see potentially this binary black hole merging for years, months, days, and then it would merge, and then it would ring down in the LIGO band. So we have the potential, depending on the mass of these signals, to watch them for a very long time with LISA. And that means you'd get exquisite details about the black hole binary in spiral. Yeah, so this LISA will run for about, say it's in there, say it's floating, whatever satellites do, orbiting the sun for about 4 years, taking data, then it would potentially be able to see this signal 4 years before merger. Yeah, that's the this part or this?
That's the limits of the observer.
Yes. This is the limits of the observatory. Oh, the wiggles, I don't remember. Anyone remember why LISA wiggles like that? Oh. I don't know if that's the orbital problem. I can't remember why it wiggles. That's terrible. No one remembers. We can Google it, though, and I'll tell you. Or I'll call someone. Call a friend. Why does LISA wiggle? I know the reason. I've forgotten. Yeah, so because, and so you'll see it for the whole point why we're so excited about LISA is because you see way more black hole binaries, but you also see them for so long. So you really think you could test GR. And I have this plot up here because I was excited about multi-band gravitational wave detection. So these are just some examples where you would see it both in LISA and in ground-based detectors. And it gets really messy here because these are unequal mass ratios at crazy inclination angles. But that's probably too much detail for you guys. But the point is, not only would we see a ton of binaries at different masses in LISA, we could potentially also see them here, and then we'll see them merge later, the same signal in a ground-based detector. So there's just like a bigger region of what we can study in the future. So I'm going to stop. I'm going to stop and just talk a little bit about summing up what I think we should be doing. So what do I want you to take away from this? You're going to I took away inclinations hard and I don't understand double chirp. So success. No. I want you to understand that gravitational waves are improving. And because they're improving, that's going to put pressure on numerical relativity to be better and better at solving the equations. Not only how accurate we are in our number of cycles, but also in going towards high mass ratios, et cetera, that we want to be able to tackle. And that becomes a regime where I'm not even sure if it's improvements in numerical relativity or something else we haven't thought of between numerical relativity and perturbation theory. I hope you understand that numerical relativity is important as we do gravitational wave astronomy, and that there are several computational techniques and different methods to do the equations that I'm hoping you guys know something about. Because we need to understand how to fix this high mass ratio problem. We need better computational methods for scaling. We do this not well right now. And there's a lot of active research, not by me, on different methods that you can do for these equations that might help us beyond these points. But we need a revolution somewhere right now to get beyond what we're currently doing. So I think that's pretty exciting because we're talking about in the next, no longer can we don't have to guess when this is going to be important like we did in 2002. We didn't know when we might see these gravitational waves. Now we know we're going to see it, so I think the investment's worth it. Thank you. But now we're late, see? Yes. Sure. So the thing is that, well, let's go to this plot. It might help. When you have a picture like this one, whoops, that guy here. No, see? My iPad's too tricky for me. When you have something where you have one black hole is much bigger than the other, we really need to resolve this gradient. This is the curvature basically increasing, and the black hole singularity is there, and the second black hole singularity is here. And the problem is that you're at the mercy of the smallest scale for resolution. How many points you're going to actually compute across the black hole is the scale we have to worry about. And so the small one means that we really have to do an incredible amount of resolution to capture that, and then that dictates what our grids look like as we go out. So it's just computationally expensive. And at some point, I just don't think our techniques right now will work to do it the way we do the mass refinement. But it really is just a matter of scale of that little black hole. We do it anyway, even for the equal mass. We still have to do adaptive mesh because we still have to resolve the black hole and detect the gravitational radiation with enough points across it to be viable, to be well resolved. But as that black hole shrinks, you really increase the problem, and it becomes unattainable.
But it's not proper adaptive mesh refinement. I mean, we use these fixed boxes to move around with the black hole.
These boxes here. So.
And the geometry of these boxes is not conforming to what I think one should have in this situation, which is more of a spherical looking kind of board. Is it adaptivity or is it a multi-scale?
It's adaptivity along the line of Marshall-Berger's type of thing, isn't it?
Yes. The part of the problem is that because the scales don't disappear, I mean, you always have to resolve this black hole. So it's not a situation like in turbulence where you might need more resolution at some point and then not. These black holes are always there. So in that sense, fixed mesh makes sense because you always have to follow this black hole. But at the same time, you have to resolve the radiation going out. So that's where I think it's tricky because the scales don't disappear and come in and come out. Yes. Right, but we don't need fine scale absolutely everywhere. We need, it can be adaptive in that we don't need as fine of scale out here as we need in here. So that's why we use this type of adaptive. Mm-hmm. Yeah, even a current generation can detect supernova, but only in our galaxy. So what happens is the detectors, core collapse supernova aren't as strong because it's a single object asymmetrically collapsing. So my comic about the two things is just the strongest way to get a lot of power in your gravitational radiation. So you absolutely can detect supernova if they happen. If Betelgeuse goes, LIGO will see it and Virgo will see it. But I actually don't know how much better we get when we go to advanced LIGO. Lisa's not going to be good at seeing. The space-based ones are in the wrong frequency band to see the supernova. So we still need that ground-based at about a few hundred hertz to see those babies. They should get better, though. He'll get more sensitive, so our chances go up as the detectors get better.
Okay, so we're studying the stars for this kind of workup. We had a talk, we need a break. Plenty of time to continue discussing that, and we'll meet again at 11 o'clock sharp with my boss.
And we will Google about funny Lisa things. I don't remember.